Good to see everyone. No one would mistake me for an applied mathematician, but today I'm going to talk about an applied project. This is a neat thing that I discovered a few months ago. It's the answer to the question, how much string to string a cardioid? So the cardioid is one of the most beloved curves in mathematics. One way to think about this is rolling a circle around a circle of the same size and watching what one point traces. There's lots of ways that you can see this in the Mandelbrot set, in the bottom of your coffee cup. You can see it using circles on the left. And today we're going to talk about the lower right example that it can show up in string art. So if you've not seen this before, the idea is to take a circle, divide it up into numbered, evenly spaced points, and you connect each numbered point to twice that number mod whatever the number is. So in this example, this is 54 equally spaced points. And you can see on the left where these lines are drawn. If you didn't multiply by 2, but multiplied by a different number, you get some other shapes. So we have the cardioid, the nephroid, and some other pretty shapes here with different multiplicative factors. It also does not depend on how many points you have around your circle. This is an animation with 1 through 100 points. The only thing that really changes is how clearly you can see this envelope of lines for this cardioid. I'm going to say a couple words about something that I talked about at the Bridges conference the last time. And here the question was, what if you wanted to make one of these cardioids using string, but you didn't want to have to keep stopping and starting and cutting off new pieces of string? Could you go from one number to the next, to the next, to the next, and string it with one string? And so in short, you can, but you have to be careful. The number of points on the circle has to be a prime number, but just being prime is not good enough. The number a, that's your multiplicative factor, has to be something that the algebraists call a primitive root of that prime number. This table here has the prime number of holes across the top and the multiplicative factors on the side. And in the center is how many pieces of string you would need to make the cardioid. So the ones are all the good ones. Those are the ones you can do with one string. So this is not what I'm going to talk about today. But for the rest of the talk, I will, just for simplicity, assume that we do have a prime number of holes. These are the ones you can string with one. Oh, you have to at least have a prime number of holes to string it with one string. So the question is, how much string do you need? So if you really want to make one of these with string, you need to start with a piece of string. So how long does that string have to be? This was the question that I was trying to find the answer to. So here's how I thought about it. We could take our numbered hole j. We're connecting it to aj. So for the cardioid, a is 2, remember? And so the distance between those two holes, counted in terms of these numbers, is a minus 1 times j. And so if you look at all of those little line segments, they're going to have length 0, length a minus 1, twice a minus 1, 3 times a minus 1, and so on. But remember, our assumption here is that n is a prime number, right? So if n is a prime number, these are just the numbers 0 through n minus 1 in disguise. So this is just some algebra number theory. And so in terms of lengths, that's what we need. And so the next question is, how long are these chords on this circle? Okay, well, if we look at a little bit of geometry here, if our central angle is theta, let's say, and the radius of our circle is r, then the length of the chord is 2r times sine of theta over 2. But in our case, we're talking about the distance between these holes. So the angle is going to be some multiple of 2 pi over n. So they're going to have that form. And so if we're looking for the string that goes, that has distance j mod n, it's going to be 2r sine pi j over n. So that's how long one of those chords is. And so the amount of string we need is this sum. So that's cool. That's actually something you could compute. You could plug it into Wolfram Alpha if you know what your radius is and you know how many holes you have. And so this could, and I thought was going to be the end of the story. Because surely there's no nice closed form for this summation, right? So the next thing I did was went to Wikipedia. I was looking at like trig identities and whatever. And I found this lovely identity by Lagrange, which was just exactly what we needed. So the sum of sine Jn from j equals 0 to m is that expression on the right. There's a few different ways you can write it, but this is the one that's going to be most useful to us. So here's the length of the string we need. That's what we get when we apply Lagrange's identity. Then you do a little bit inside those parentheses. You use some properties of the sine function. And our answer is 2r cotangent pi over 2n. So that is pretty cool. So yeah, pretty awesome. That was pretty awesome. But the awesomeness does not end, actually. So this is the amount of string you need. A doesn't show up in this string at all. So these all have the same number of points around the boundary. They need the same amount of string. So the two on the left are these sort of traditional multiply by 2 or multiply by 3. But you could as well just think of them all coming from a single point, and you get this sort of sunburst shape. And those all require the same amount of string. So here's an example. I had to test it out. I don't trust myself as an applied mathematician. So I made this and 3D printed it. This one had a radius of 4.8 centimeters. Oh, I'm out of time here. So this had required 617 centimeters of string, and it worked. And this is your gift exchange item with a 3D printed ring, the right amount of string, I hope. And you can make, it has 53 holes, so you can make either the cardioid or the nepheroid. And that's a good place to end. Thank you.
Thank you very much.